one of my friends slides, he gave me this slide. This is not a picture of a galaxy. This is the picture of a tumor microenvironment. If you look at very carefully, if you take the tumor and if you look at very carefully, only you will find that 25 to 30% of the tumor mass is the tumor cell. Rest of them are not tumor cells. All of them are stromal cells. They are mostly immune cells and some of these cells, fibroblasts and other cells. So why these immune cells or the other cells are there in the tumor microenvironment? What they are doing? That is very interesting. And that has been very nicely described by Bob Schreiber, one of my collaborators, and he wrote a very nice article in Nature Annual Review of Nature Immunology. Here he described why these cells are there. See, this is a normal tissue, and there are some factors that can cause to transform the cell into the transform cell. And we have a natural hardware or immune system that can tackle, that can recognize these transform cells, and they can, they can act on that, and we get the immunization because we don't develop tumor. And that is what happening to most of the people. Those are fortunate, they don't develop tumor. But there are some certain people who are not that much fortunate. In that case, what is happening, this tumor, they get another types of mutation. The mutation burden increase, and these cells become very smart. What they do, they mask their antigen, surface antigen, so that our immune system cannot recognize. And by that way, they can remain in our body for years. And whenever they find that there is a problem in the immune system, there is a suppression of immune system, that is maybe because of the aging, that may be because of the overdoses of antibiotics or immunosuppressive drug. As soon as they see that there is a problem in the immune system, these cells start proliferating very fast, and they overpower our immune system. And they control our immune system, they make them in favor of the tumor and help them the tumor to grow, and outcome is the tumor growth. So this is what is happening in our body. So I was very much interested to find out how this tumor escaped from our immune regime. So we did lots of work on that, and we tried to find out how the tumor microenvironment plays very important role. They overpower our immune system, and they overpower immune system by different way, by suppressing the immune function. They convert them to type 2 immune system. They kill the cells. They erase the memory of the central and memory immune system, so that they cannot recognize this. Our immune system cannot recognize it's a disease cell. They block the cytotoxicity. They block the proliferation. They develop one type of cell that is called T regulatory cell in tumor microenvironment. So by that way, they escape our immune system. We are trying to find out how they are doing. So main reason for the failure of the immunotherapy, if you look at, so if you develop some tumor, we go for the chemotherapy, either chemotherapy or genomically targeted chemotherapy. And we find that this therapy can kill the tumor cells. And we publish the paper, we are happy with that. So, but there is one very small fraction of the cells which are called drug surviving cells. Recently it was known that these are the cancer stem cells. So they are escaped from this chemotherapy or genomically targeted chemotherapy regime. And these cells are the reason for the tumor relapse. They are highly drug resistant. We hope that our immune system will be able to, by help of this immunotherapy, will be able to recognize the cell, and this so that they can target the cell and will stop the relapse of the tumor. And that is what is happening in the rest of the 20% of the patient. And we publish papers. That's our goal, first goal. So, but the problem is that during the tumor development, what is happening? The tumor produces lots of factors, and they change our immune system, which are immunogenic cells, they make them tolerogenic cells. They change the status of this immune system. And this tolerogenic cell, they cannot target these drug surviving cells. That's why if you protect our immune system, what types of immune system we are protecting? We are protecting the type 2 immune system. which helps the tumor to grow more. That's why when the patient, they are given the immunotherapy, if the immunotherapy fails, the patient dies faster than the normal course. So this tumor becomes more aggressive if the immunotherapy fails. So what is happening? This tolerogenic, we are going to protect this tolerogenic cell, and they fail to target this immune cell, and this drug surviving cells or the cancer stem cells, and they become more aggressive and they relapse very fast and patient die. So if you can rejuvenate our immune system by different way, so that if we can make them again more immunogenic, we'll be able to target them, and these drug surviving cells, they will die. So we are trying to find out how we can make them immunogenic. So to understand how these immunogenic cells are becoming tolerogenic, we did lots of experiments and try to find out. We identified one type of T regulatory cells that are specific for tumor. They are quite different than the other T regulatory cells, and these T regulatory cells are highly IL-10 producing, they are very aggressive, and they produce lots of other factors that help the tumor to grow. So we found that these cells are also CTLA4 positive, and they are quite different than the normal T regulatory cells, which are, I think this slide is not working. These are the normal T regulatory cells, that is the inducible T regulatory cell, and if you look that these are the tumor specific T regulatory cells. They are quite different than the natural T regulatory cells. And we found that they have these T regulatory cells have both the beneficial and the detrimental role. These tumor-specific T regulatory cells are detrimental. They have a detrimental role. They suppress our immune system. They help the tumor to grow. So we have found that this peripheral T regulatory cell and these are the tumor T regulatory cells. They are quite different than the they are quite different than the peripheral T regulatory cells. And these T regulatory cells are really immunosuppressive because they cause all sorts of function that can suppress our immune system. Not only that, they are so aggressive. They produce lots of rankle types of protein which cause the tumor metastasis. They produce lots of VEGF that can cause the neoangiogenesis. And this is the reason behind the tumor is making more aggressive. So we found that in tumor microenvironment, if we have a low number of T regulatory cells, our immune system can recognize and eliminate our tumor. If these T regulatory cells are fluctuating, this immune system and tumor, they remain into the equilibrium condition, and they can remain for even sometimes for 20 years in our body. And if you have a high level of this T regulatory cell, that can cause the immunosuppression and the immune system, that can cause the immune system in favor of this tumor, we see that the tumor escape from the immune system and we develop tumor. So if this is a high-grade tumor and low-grade tumor, you see that T regulatory cell is a high number in the tumor microenvironment. Sometimes nearly 20% of the tumor total mass becomes the T regulatory cell. 20%. So you can understand how big this T regulatory cell. And if you look at the overall survival, if you have low T regulatory cell, you see this 20% of the patient, they survive because they respond to this immunotherapy. And you see this 80% of the patient, they don't respond to the immunotherapy. That maybe that in addition to the other factor, T regulatory cell plays very important factor for the non-responsiveness of the tumor, this immunotherapy. So we try to find out that because these T regulatory cells, they are coming from the blood because of the tumor produce lots of factors that can produce these T regulatory cells, and they have the CCR4 chemokine receptor that can target them to the tumor sites. So they produce into the peripheral circulation and go to the tumor sites and help the tumor to grow and suppress the adjacent immune system like macrophage or Th or NKT cells, so that they can overpower this immune system and help the tumor to grow. So this T regulatory cell has one common factor. that is that they have a specialized lineage-specific transcription factor, which is a FOXP3, and this FOXP3 can act as a suppressor, repressor, and the activator of the transcription. And they are, so we are trying to stop the development of this T regulatory cell. We found that they have this. If you want to stop the development of T regulatory cell, you need to stop this transcription factor simultaneously at the same time. If you stop one, the other factor will help the development of this T regulatory cell. So if you want to stop the development of this T regulatory cell in tumor microenvironment or in tumor condition, you need to have a battery of drug to be used. But by using the battery of drug, we can stop the development of this T regulatory to make the patient susceptible for immunotherapy. But the patient will die because of the toxicity. So we have no option. So we were trying to find out the other way how we can stop this T regulatory cell. So one of the story I am going to tell today. So we did the sequencing of this T regulatory, single cell sequencing of this T regulatory cell. We found there are a number of coding and non-coding RNAs. And we use both the coding and non-coding RNA to find out the reason, what are the difference between them. First we went for the coding RNA. We found that there are difference in signal transcriptome levels in the naive T cell or Th1 cell and T regulatory cell. And we found one of the very interesting things that in effector T cells, that T cell, they use glucose as the main source of energy. You see, that their glucose utilizing enzymes are half regulated and the fatty acid metabolizing enzymes are down regulated into the system. But in T regulatory cell, if you look at, their glucose metabolizing enzymes are down regulated and fatty acid metabolizing enzymes are up regulated. So this is the different factor. Can we target this by their diet? So we found that this T regulatory cell, they express high level of CD36, one of the protein which is a scavenger receptor that binds fatty acid to internalize and help the metabolizing of fatty acid. So we found that this.
Professor Gauri, sorry to interrupt. Your time is up actually.
Yeah, I'll finish.
Just summarize. Thank you.
So I will not go to the details how this transcription factor upregulated this protein with CD36. But what interesting is that this T regulatory cell generation depends on the fatty acid metabolism. And what is happening in tumor microenvironment, you see, tumor mass, they use most of the consumed glucose used by the tumor cells, and the less amount of that effector T cells which are which act against the tumor, they don't get the glucose because these tumor are very aggressive. They use most of the glucose, so these effector cells die. But in case of these T regulatory cells, since they have the alternative CD36, they utilize fatty acid for their metabolism and for their survival. And so these cells, they survive. And now if you see, if you can change your diet, if you use the low fat and high glucose diet, and then use the chemotherapy, you see, this is the tumor alone. If you grow them, if you let the mice take the low fat and high glucose diet, even without the chemotherapy or immunotherapy, you see the tumor size is smaller. And if you give them the chemotherapy along with the this low fat high glucose diet, you see the chemotherapy works better. If you give them high fat diet and chemotherapy, you see that you can compare the tumor size. Just changing the diet, you can increase the efficacy of the chemotherapy. And you see, this is the efficacy of the immunotherapy can be changed. You look that this is a normal tumor, and this is the high fat diet, this is the low fat diet. This is the normal tumor, only given the immune checkpoint inhibitor therapy, immunotherapy, you see the tumor is smaller. But if you look at this one, if you give them the low fat diet and give them the immunotherapy, you see, you compare this with the high fat diet or the normal diet. If you give them the low fat diet and high glucose diet, during the chemotherapy, the immunotherapy or chemotherapy that works better. I think I'll stop over here. I will not discuss the non-coding area.
Yeah, thank you, Professor Gauri Shankar.